Hello guys, welcome to this new video. So this is going to be question 3 in the May 2023 Time Zone 2 paper 2. So here we're given a blue light of wavelength lambda. It is incident on a double slit, and light from this double slit falls on this observation screen, and we're given 9 successive fringes on the screen are 15 centimeters apart. We're given the separation of the double slit and the distance from the double slit to the screen. So just the standard information for a slit question. And so in the first part, we need to explain the pattern seen on the screen. Well, first of all, what is happening here is that when the light travels through this first slit, we're going to have this interference pattern. And then when they travel through these two other slits, they're going to further diffract. So it's going to look something like this. And these two waves will be interfering, and when they reach the screen, a so-called interference pattern will be observed. And we will see bright and dark fringes. So, I mean, we need to explain what we see on the screen. So the proper answer is just to say that we see bright and dark fringes and explain a little bit about them, why we see them. So we see bright fringes because the waves can superpose when they are in phase. So when they are in phase, their amplitudes add up and they amplify each other, increasing their net amplitude, their net intensity, and that's why we're going to see a bright fringe. And then the opposite of this can happen, where we see a dark fringe. That's going to happen when they superpose, but they are out of phase. So they will kind of cancel each other out. Out of phase. So for example, the peak of one of the waves meets the trough of the other wave, and when these 2 points meet, they will cancel each other out and form a wave of zero amplitude. And at given distances, these will be observed on the screen. So for example, there will be maximums over here, and in between them we will have the minimums where there is no light observed. So this will likely be needed for the 3 marks. And then in part B, we need to calculate the wavelength. So here we always need to be careful a little bit because they didn't give us the fringe spacing. They told us that between 9 consecutive fringes, there was 15 centimeters. So what I would recommend is to draw down these fringes and count what this actually means. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And we know that this is 15 centimeters. But we cannot simply do 15 divided by 9 because that is not going to be the fringe spacing. The fringe spacing will in fact be 1 less because fringe spacing is always the distance between 2 maximum. And if we count how many there are, there's 1 here, 2, 3, 4, 5, 6, 7, 8. So there's only going to be 8s. So our fringe spacing, our S, fringe spacing, S, is going to be, well, if we convert 15 centimeters to meters, it will be 0.15 over 8. And then now we can simply use the well-known formula of S equal to lambda big D over small d, where S is the distance between 2 consecutive maximum, lambda is the wavelength, big D is the distance from the screen to the slits, and small d is the distance between the slits. And we are given both of these values. So if we simply rearrange for lambda, we will see that lambda is S small d over big D, and then we just plug in the values and we find the answer. That's 0.15 over 8 times small d, which is 6 times 10 to the minus 5 divided by 2.5 meters. and we will find that the wavelength is 450 nanometers, like this. That is part B1. And then in B2, there we are told that the screen is moved closer to the double slit and the measurements are repeated. The instruments used to make the measurements are unchanged. This is very important, which will come up here. And we need to see the effect this has on the fractional uncertainty in the value of lambda. So first of all, let's recall the formula we just used. So lambda was S small d over big D. And if all of these values have a fractional uncertainty, then technically what a fractional uncertainty is, fractional uncertainty is just the absolute uncertainty divided by our measurement. And the absolute uncertainty is usually a property of the instruments we use. So for example, a ruler has a given absolute uncertainty. A weighing scale has a given absolute uncertainty. So this is going to be unchanged when we talk about this in our question. Unchanged. This will be key. And so if we want to find the uncertainty in lambda, and we make measurements for S, small d, and big D, then we need to propagate this uncertainty we have in S, small d, and big D. And since you're doing multiplication and division of uncertainties, the way we can do this is by adding the fractional uncertainties of each of these measurements. So the fractional uncertainty of wavelength is what we need to find. So that's just the absolute uncertainty divided by the measurement we make. This will just be the sum of all of the uncertainties. As I said before, if we're just adding or dividing values, we just need to add their fractional uncertainties. So we just need to list all three of them and add them together. Oops. And change in small d over small d. So as I said here, that these, well, this is just unchanged because we're not changing anything about the slits. So the distance between the slits will not change, so we don't really need to account for that. But this S and D will change as we're bringing the slit closer, and therefore these fringes will, the spacing of these fringes will change. They will become smaller. So this D becomes smaller, and therefore this S also becomes smaller. And as I said at the start, these are unchanged because the probably ruler we are using to measure these has still the same scaling. For example, a scaling of 0.1. It has a scaling of 1 millimeter, so the uncertainty is just half a millimeter. That is unchanged. And therefore, these two fractions will become overall larger since we are decreasing the denominator. So the fraction will be larger since the denominator is decreasing in size. And if the fraction becomes larger, then if the right side is increasing in size, then the left side of the equation must also increase in size, and therefore the fractional uncertainty in the wavelength will also increase, like so. All right, and then part C, we are told that the student changes the light source to one that emits two colors now. One is still the regular color we were using of blue light, wavelength lambda, and a red light of wavelength 1.5 lambda. And we need to predict the pattern that we will see. Well, we're still going to see an interference pattern, but we will see both the interference pattern of the blue light and the red light. So we will see pattern of blue and red light. So pretty much like two separate experiments, it's just that they are combined into one. So we will see the pattern of both. And Well, the spacing of blue, so the fringe spacing of the blue color, will remain the same because we haven't changed anything from our initial experiment. So for this, it's unchanged. But since red light has a wavelength that is larger, and we know that the fringe spacing is just lambda big D over small d, so if we increase lambda, then our fringe spacing will also increase. So the red light will have larger fringe spacing. Like this. Because if we would plug into the formula, it would be like 1.5 times the original lambda times big D over small d, and so the fringe spacing must be larger. And so we will observe these two patterns separately on the screen, and then there will obviously be regions where these two patterns overlap, and where they overlap, so where the bright fringes of both colors overlap, we will see purple. As that's what happens when a red and a blue light overlap. And so, yes, that was question 3 in the May 2023 time zone 2 paper 2.